Lesson 3.2, Force System Resultants, the sequel. In this lesson, you're going to learn how to determine the moment of a couple, the moment of a force couple system, and then you're going to reduce a system of forces to a force couple system and to a single force. So what we're going to be doing in this lesson is taking what we've learned with forces and with moments in previous lessons and start being able to manipulate forces and moments into simplified systems so that we can more easily analyze complex systems. Here's a good example of a force couple. On the lug wrench shown, changing a tire, you apply equal and opposite forces of F. So what's the net force that you've put on the wrench? Are you pushing the wrench down or pulling it up? No, you could say, well, maybe you're pushing it down on one side and pulling it up on the other side. But if it's with equal and opposite forces, you're really not doing any pushing onto the wrench as a whole. What you're doing is you're actually putting a twist on it or a moment. And so a force couple is a particular case of forces. All right, it's a little subset of forces that exist all over the place. This lug wrench would be a perfect example. But a force couple is a pair of forces. That's what a couple, right? A pair of forces equal in magnitude, opposite in direction, and there is a perpendicular distance between them. That's the definition of a force couple. So here is what that might look like when you're changing a tire. Maybe you're pushing down up here on the top, pulling up from down there on the bottom. We looked at this in a previous lesson, but we only had the force in one spot. Now we're doing it at both ends here. And so if you want to take it about, the moment about the center axis like we did in the last lesson, counterclockwise positive, you could say that the moment caused by these forces might be this force F multiplied by d over 2, which is this distance. And that would be counterclockwise, so positive. And then this force down here times d over 2. And it would also be a positive moment because it's also wanting to twist this counterclockwise. You add those two things together and that you get this moment to be F times d. And that works also if you take the moment about this end of the wrench up here, because now you're going to have this force not generating any moment because it's acting through this point. But you're also going to have this force down here acting at a full distance of d away. So it would, again, be F times d counterclockwise. And even if you looked at this point down here, and now this force is not causing a moment because it's acting through the point. But this one up here, F times d counterclockwise. So either way, you're going to get actually in all three cases, here, here, and here, it's all going to be just F times d. And as a matter of fact, if you do it about any point in space, these two forces will generate a counterclockwise moment of F times d, which is a really neat concept here. These two forces don't actually have any net force, right? Because they cancel each other out. If F is pointing down and to the left up here, it's up and to the right over here. They cancel each other out. So there's no net force. It adds a moment, and the moment is a free vector. And so a free vector means it has an orientation, but no point of application. You can have it be anywhere. It's just, in this case, it would be a counterclockwise moment of F times d. Here you have a steering wheel. You're 9 and 3, right? Because you're driving with both hands. And when you do that, and you're going to be turning left in this instance, you're going to push up with your right hand and pull down with your left hand. That distance between them of d, you're going to have a moment of F times d, just like the previous slide. I think every car has power steering these days. It was an added feature a long time ago. But it's, you have a system that aids you in turning the steering wheel, so the steering wheel will be easier to turn. That's what power steering is all about. If you didn't have that, do you think you needed a smaller steering wheel or a bigger steering wheel? Well, they had bigger steering wheels to help without power steering. They had bigger steering wheels in the absence of power steering because you needed that additional help. The bigger the distance d, the same force F is causing more moment. So it's going to be doing its job better. It's going to be twisting the steering wheel, turning the steering wheel, and causing you to turn the car. All right, that's a force couple system. Here's another force couple system, right? Here's another force couple system. Equal forces opposite in direction with a perpendicular distance between them. And you can look at it from a scalar point of view or a vector point of view. So this one up here is kind of the scalar point of view, and this one's the vector point of view. From a scalar point of view, it's just going to be the magnitude F. They're always equal and opposite, so you say which one? Well, it doesn't really matter, right? Because it doesn't matter which side you look at. This is going to be a counterclockwise moment of F times D, where D is that perpendicular distance between them. Now, it's a little bit different looking in vector, but vector is always different looking, but when you really start doing the numbers, you see that a lot of the numbers are actually the same. In vector formulation, what you do is if you have two equal and opposite forces like we have here, you need to do R cross F, just like we always do. But you're going to do R from the point of application of one of the forces to somewhere along the line of action of the other force, which is often the point of application, as you see here. Okay. And so R cross F for us here, if you're going from R starting down here and going up to this vector, then the F vector that you need to be analyzing in R cross F is actually the vector you ended at. Wherever the arrowhead of your position vector ends, that's the F you need to be looking at. From a scalar point of view, they're the same magnitude. From a vector point of view, they're the same magnitude. But if you actually do these two forces F as Cartesian vectors, if you're looking at it in vector form, they all have the same numbers, I, J, K, but all of the signs are flipped. So you have to pick the right one. And so if you're going to do R cross F and you're starting R here and ending there, then you need to pick this F. If you're doing it the other way, you start your R here, you go down to this vector F, then you're going to be picking this one. And I think you can probably see, why you have to pick the right F, because your R, if I flip the R, I also get the different signs for that. So you really you end up getting the same answers. You just got to make sure you have the right set of R and F to look at. So the net external effect of a couple is that the net force equals 0 and the magnitude of the net moment equals F times D. Since the moment of a couple depends only on the distance between the forces, the moment of a couple is a free vector. It can be moved anywhere in the body and have the same external effect on the body. Couple moments are vectors. Moments in general are vectors. They can be added together using the same rules as adding any vectors.